The ground moves before you hear it. Not the subtle tremor of a passing truck, not the distant percussion of a construction site, something far slower, far more total. A vibration that rises through the soles of your boots and into your chest, like the earth itself has a heartbeat. Then you see the shadow. It rolls across the open pit in the brown coal country of western Germany, a shadow so wide it swallows the light from horizon to horizon, cast by something so enormous that your brain initially refuses to categorize it as a machine. It looks more like a coastal cliff that has decided to migrate. And at its leading edge, spinning with quiet, almost gentle regularity, is a wheel of steel buckets roughly the diameter of a 5-story building, biting into the earth in one long, continuous, unhurried revolution. This is the Bagger 293. And the question is not how big it is. The question is how something this big actually works, and why, once it starts moving, the engineers who built it designed it so that it almost never has to stop. Because when you stand in front of a machine that is 96 meters tall, 225 meters long, and weighs roughly 14,200 metric tons, a machine that can move approximately 240,000 cubic meters of earth in a single day, the instinct is to assume that the secret must be equally massive. Some titanic engine, some impossibly powerful explosion of force. But the trick at the heart of the Bagger 293 is almost the opposite of that. The trick is patience. The trick is continuity. And by the end of this, you will understand exactly why a rotating wheel and a moving belt are, together, more powerful than any explosive or any army of workers that has ever broken ground. Start with the soil. The Bagger 293 operates in the Rhineland lignite mines of western Germany, specifically in open-cast pits where the overburden, the rock and clay and soil sitting on top of the coal seam, has to be stripped away before any fuel can be extracted. Lignite, sometimes called brown coal, sits in layers that can run dozens of meters deep, and the ground above it is not soft. It is compacted glacial till, clay, sand, and sediment laid down over millions of years. To reach the coal, you have to remove everything above it, sometimes moving it kilometers away. The question facing German mining engineers for most of the 20th century was not whether this was physically possible. It was whether it could ever be done fast enough, continuously enough, cheaply enough to make the energy economics work. And the answer they arrived at was not a bigger shovel. It was a wheel. The bucket wheel is the core mechanism, and it is worth understanding exactly what it does and why. Imagine a Ferris wheel, roughly 21 meters in diameter, but instead of passenger gondolas, it carries 18 steel buckets, each one with a capacity of roughly 15 cubic meters. That wheel rotates continuously, driven by electric motors, at a speed carefully calibrated so that each bucket scoops into the earth face, fills, rises to the top of the arc, and then tips its load onto a conveyor belt position directly behind the wheel. The bucket empties by gravity. The wheel keeps turning. The next bucket enters the earth. This cycle repeats without pause, without the downtime of a hydraulic excavator swinging its arm back, without the reset time of a dragline reeling in its cable. There is no stroke and return. There is only the wheel, turning, always turning. Now consider the math. 18 buckets, each holding roughly 15 cubic meters, on a wheel rotating at a rate that delivers continuous, uninterrupted flow onto the conveyor. The result is that the Bagger 293 can move material at a rate of roughly 240,000 cubic meters per day. To put that number into a shape your mind can hold, a standard American football field is roughly 100 meters long, roughly 50 meters wide. If you dug out that football field to a depth of 48 meters, roughly the height of a 15-story building, you would have moved approximately 240,000 cubic meters of earth. The Bagger 293 does that, every day, as a matter of routine. Compare this to what came before. In the mid-20th century, before machines of this class were developed, open-cast mining at this scale required thousands of workers, networks of railway-mounted shovels, and blast-and-load cycles that were inherently discontinuous. A blast loosens material, workers move in, shovels load rail cars, trains carry the spoil away. Every step in that chain has a pause, a reset, a vulnerability to delay. The Bagger 293 eliminated the pause. The conveyor system that runs from the bucket will back through the machine and out across the pit is not a simple belt, it is a linked network of conveyors extending kilometers beyond the machine itself, carrying spoil continuously to the overburdened dumps on the other side of the pit. The entire system, from wool to dump, operates as a single continuous flow. In engineering terms, it is a pipeline made of moving rubber and steel rather than pipe and fluid, and like a pipeline, its efficiency depends entirely on never stopping. This is where the false belief needs to be corrected. Most people looking at the Bagger 293 assume that the machine's power comes from brute force, that it must be driving those buckets into the earth with enormous pressure, the way a hydraulic ram drives a pile into the ground. But the machine does not ram. It does not punch. The bucket will advances by moving the entire machine laterally along its crawler tracks, pressing the rotating wheel gently but relentlessly into the earth face. The cutting action is more like a cheese grater drawn slowly across a surface than a hammer driving a nail. The earth is not fractured or blasted, it is continuously sliced away in thin layers as the wheel turns and the machine inches forward. The force required per bucket is actually quite modest. What makes the system capable is not the force per cut but the total number of cuts per hour, sustained without interruption across an entire working day. The crawler tracks deserve a moment here. The Bagger 293 does not roll on wheels. It moves on 12 crawler track units arranged in groups beneath the machine's three main support structures. Each individual crawler track unit is roughly the size of a city bus. The total ground contact area of all 12 units together is large enough that despite the machine's 14,000 plus metric ton mass, the ground pressure it exerts, the weight per unit area, is actually lower than that of a human being standing still. That figure sounds impossible until you work through the geometry. A person exerts all their weight through roughly 300 square centimeters of shoe sole. The Bagger spreads 14,000 tons across many thousands of square meters of track contact. The result is a machine that can cross soft ground without sinking, moving at its operational pace of roughly 10 meters per minute, slower than a walking human, but relentless, constant, day after day. Which brings us to the question of stopping. Why does the machine almost never stop? The honest engineering answer is that stopping is expensive in ways that have nothing to do with the obvious costs. Every time the bucket wheel halts and restarts, the torque loads on the drive system spike. Every time the conveyor belt system stops and restarts, the tensioning systems have to be reset, and the risk of belt misalignment increases. The machine's vast electrical load, it consumes roughly 16.5 megawatts of power at peak operation, fed through cables connected to the regional grid, is actually more stable when the draw is constant than when it surges through start-stop cycles. The Bagger 293 is not a machine that was designed to be used in bursts. It was designed to be a flow, to turn or extraction into something closer to a river than a series of excavations. Maintenance is scheduled around it. The mine's infrastructure is built around it. The logistics of overburden disposal are timed to its continuous output. It is, in a real engineering sense, the clock around which everything else runs. Here, then, is the trick you can explain to someone else in one clear sentence. The Bagger 293 is powerful not because any single one of its actions is violent, but because none of its actions ever stop. Every bucket is modest. The wheel is patient. The conveyor never rests. Individually, none of these components is especially dramatic. Together, across 24 hours, they outperform any episodic machine ever built for ground removal, not through superior force, but through the elimination of every gap between one action and the next. There is something worth sitting within that. We tend to think of scale in terms of intensity. The bigger the machine, the more ferocious its operation. The Bagger 293 suggests a different logic. Its designers, working through German engineering firms in the latter decades of the 20th century, understood that in the long war against the Earth's mass, patience is a more powerful weapon than violence. They built a machine that is, in its fundamental rhythm, almost gentle, a wheel turning slowly, a belt moving steadily, a machine walking at the pace of a cautious pedestrian, and that gentleness, sustained without interruption, eats a town's worth of earth every single day. The bigger the machine, the simpler the trick that makes it work. Subscribe to see the hidden engineering behind the giants around you.